So, welcome to this licentiate thesis presentation, where Master of Science Magnus Malmström will present his licentiate thesis, Uncertainties in Neural Networks, a systematification approach. My name is Martin Enquist, and I would act as chairman and examiner at this event. Besides Magnus, the other main actor today is Professor Håkan Hjalmarsson from KTH. Welcome, Håkan.
Thank you, Martin.
And I should also add that this seminar will be recorded. Magnus' research has been supervised by three persons: Professor Fredrik Gustafsson, Assistant Professor Skog, and Associate Professor Axehill. And Daniel is here.
Good morning.
And the procedure will be as follows. Magnus will first present his work, then we'll have a short break, and after that, Håkan will lead the discussion. And finally, we will open up for questions from the rest of the audience. And after that, I will make a decision about the thesis and the presentation. So with that, I give the floor to you, Magnus, please.
Yes, thank you. Let's see when the presentation starts. So my name is Magnus Malmström. I will present this my licentiate thesis titled Uncertainties in Neural Networks, a system identification approach. And I will begin the presentation by introducing the problem and motivating why uncertainties in why it's important to quantify the uncertainties in any models, but in particular in neural networks. Then I will talk about the method we have proposed to quantify the uncertainty, then talk about the problem with overparameterization of models and how to handle that, then present some related method to do this, and then compare those between the suggested method in an experimental study, and then we will end with some conclusions. So let's begin. So in science and engineering, it's always been a central part to create models to be able to predict the future events and to be able to maybe control the events in the future as well. And this is usually done by creating physical laws, and which we then, from example Newton's law, from which then we can predict to create the models. But this can be very hard for complex systems. So an alternative approach is to use a data-driven approach, where we collect a lot of data, and we'll create a model, and then we will fit that model to the training data which we have collected, and adjust the model given some cost function. And this gets more and more attractive since it's easier to store data and easier to collect data. One application this could be useful in is autonomous driving, where it's fairly hard to model the traffic behavior, but it might be easier to collect a lot of data from driving tests. So how would we formulate this problem? So say that we are giving some noisy measurement of some signal, which is y, so measurement of the signal s. Then we aim to predict some parametric model, s hat, of both the input and the parameters. And we want to predict it such that we will minimize some cost function. And throughout this presentation, we will study the minimum least square cost function, so the squared error between the model and the measurement. But we are also interested to quantify the uncertainty, so that is seen as the red dotted lines in the plot to the right. So how certain are we that our model is correct? But why is it important to know to quantify the uncertainty in the predictions of, for example, a neural network, or any model for that sake? So even though neural networks have shown promising results in, for example, computer vision and speech recognition, they're not as widely used in safety-critical applications, such as autonomous driving. And one reason for this is it has been shown that neural networks are very vulnerable to adversarial attacks. So for example, with just adding some duct tape to a stop sign, it's been shown that the network will misclassify the stop sign as a speed sign. And we also have the problem how to handle predictions in regions where we don't have any training data. So that is how we should extrapolate to the regions where we don't have trained. And if we include some quantified measure of the uncertainty of the prediction, this will make them much more reliable in safety-critical applications. So let's motivate this with an example. So assume that we have a vehicle where we use the neural network to estimate normalized traction force, which is then used to calculate the maximum allowed speed of the vehicle. And then we will detect an obstacle 5 meters from the vehicle, and then we will be forced to brake. So here you will see the vehicle in green, which are going towards, and we will use this red prediction as our estimate of the normalized traction force, which is then used to calculate the maximum velocity. And as you can see, the measurements were quite noisy, so we were going too fast, and hence we collided with the obstacle. But we will instead include some uncertainty predictions. We will get a lower maximum speed to counteract this uncertainty, to take this into consideration. So that will be seen in this movie instead, where we are using this lower limit of the dotted line, and hence we will go slower and we'll have time to brake before the obstacle, so we will avoid the collision. So what is the contribution of this thesis and this presentation? So we are presenting a method to quantify the uncertainty in predictions from a parametric model, such as neural network is an example of, and then to handle the problem with non-unique parameterization which might occur, and then also extend the method to over-parameterized models. As well as we will compare the suggested method against methods that are commonly used in the literature to quantify the uncertainty in prediction. So part of this thesis and presentation has already been presented in the paper Asymptotic Prediction Error Variance for Feed-Forward Neural Networks, which was presented in the IFAC World Congress last year. So what is the suggested method to calculate this prediction error variance? So before we go to the method, we'll talk about some problems we will have with neural networks. So neural networks are an example of a black box model, which consists of layers of linear models combined with the nonlinearity. So here you can see the linear combination is done by this matrix W, where you combine the contribution from the layer before, which is H, and then you will take this, and then you will get this A vector, which you then will take through some nonlinearity to create a new H. And neural networks can be written as a parametric model. So that is, we will collect all these weights and biases in one long vector, which will be our parameters we can tune. So then we get it to this familiar form we saw in the problem formulation. But one problem with them is that you have a non-unique parameterization. So for example, we could interchange the nodes H11 and H12 and interchange the parameters connecting to them as well. Then the parameterization will look completely different, but they will be exactly the same prediction of output. So how should we know which one of these parameterizations we should choose? So how can this be handled? So first you can see this, if you simulate a measurement of normalized traction force given this wheel slip, and we have a minimal network, which is the minimal size of the model needed to represent this data. And that is a 2-layer neural network with 2 nodes in the hidden layer. And if we train 200 realizations of this, where we only change the initialization values, which can be seen in the lower figure on the left, where the initialization values are the small crosses and the final values of the parameters are the circles. You can see that they will end up in 8 different clusters, depending on the initialization. And it's not really clear where this parameters ends up. So if you, for example, check one of these small green dots, they might be closer to one of the yellow clusters, even though they will end up in the green cluster in the end. So how should we handle these ambiguities in the parameterization? So if we go back to the problem formulation, as seen before, so we have some noisy measurement. We want to estimate a model for this noisy measurement that of minimizing some cost function. We will talk a lot about the prediction error, so that is error between the model and the measurement. And to counteract these ambiguities, we will assume that we have a unique parameterization for these minimal networks, which is called a canonical representation, and will be denoted by subscript C. And given this non-canonical representation, given any other parameterization, so say that we have used the green clusters as our canonical representation. If you would get any of the other clusters instead, it will be, we could go from that cluster to this canonical by transformation Ti. So now we're ready to present our method to quantify the uncertainty predictions for a parametric model of, for example, neural networks. So assume that the true system is in the model set and it's represented by the minimum model. So that is that the model is flexible enough to represent the system that has generated the signal, but we don't have too much flexibility. Then given finite number of noisy measurements of the signal, the prediction error variance of the model is given by the derivative of the canonical model with respect to its parameters times the covariance of the parameters times the derivative of the model with respect to its parameters transposed, where the covariance of the canonical parameters is given as 1 over n times the prediction, an estimate of the prediction error variance times the inverse of the information matrix, where the information matrix is a rolling average of the derivative of the canonical model with respect to its parameters transposed times the canonical model. But we did a choice here, which parameter we were considering to be the canonical one. Does this choice matter? So another way to phrase this question, are all the parameter covariance equally uncertain, or are all the different parameterization equally uncertain? So to compare this, you can calculate the eigenvalues of the parameter covariance for the different clusters. And they have been plotted in ascending order on the right. And two measures of how uncertain the parameter covariances are is the determinant and the trace of the matrices. And that is basically the product of the eigenvalues or the sum of the eigenvalues. And they are shown in the legend on top of the figure. And it's the same color coding for the clusters as seen before. And one can see if one studying the trace and the determinant, it seems to be the same for all the different clusters, and that can also be seen if you're just studying how the plot looks like. So it seems that they are equally uncertain. But how is it about uncertainty in the prediction, which is a thing that we actually are interested in? So for a minimal network, the transformation from canonical parameters or from any other parameter to the canonical parameters will be a quadratic matrix Ti, which will be invertible. So then using the chain rule, we could write the derivative of any other parameterizations as a function of the derivative of the canonical model with its times its parameters. And they do the same for the parameter covariances. And then we can show that the prediction error variance for any other clusters is equal to the canonical representation if the network is minimal. But does this hold without the knowledge about this minimal representation? So now we come to the problem with overparameterization. So in practice, overparameterized neural networks are often used. And then the transformation Ti might decrease the size of the parameters, which lead to singular or close to singular parameter covariance matrices. And hence the linearization method has to be modified to take this into account. And to do this, we will divide analysis into two steps. So first, we will consider redundant parameters, which is parameters that doesn't add any more flexibility to the model. So they could, for example, a linear combination of the parameters you already had. Or then we will move on to the more general case where we have a more flexible model. So if we start with redundant parameter, and we start with the simplest case. So that is, we have a model that is linear in the parameters. So that is that a model is given by some regressor vector, phi, times, which is some transformation that might be nonlinear of the input, times the parameters. And then we can estimate these parameters using the least square solution for the canonical case. And for the non-canonical case, we have to use the minimal norm solution, since there might be some ambiguities in how to choose these parameters in the best sense. And we can calculate the parameter covariance as before. So it will be 1 over n, 1 over the number of samples, times an estimate of the prediction error variance, times the inverse of the information matrix of the parameters. But for the non-canonical representation, where we have redundant parameters, we have to replace the inverse with the pseudo-inverse. So here you will replace this minus sign with a plus sign instead, to counteract the fact that we might have ambiguities and the information matrix might be singular. So if we show this with an example, so assume that we have a minimal representation with three basis function, and the non-canonical representation with 3 basis function, which are linear combination of the minimal representation. Then we generate a signal for this minimal representation, and we'll perturbate it with some noise. Then we'll estimate the model for the signal using both the representations. An important part to notice here is that they are linear combinations, so this model doesn't add any more flexibility compared to the minimal one. And then, as here on the right, you can see the prediction error variance, and on the left you will see the prediction. And if you for the canonical in blue and the non-canonical in red, and here on the left you also see the measurement in black as black dots, and you can see that it looks like the prediction, and both the prediction and prediction error variance is the same. But neural networks are nonlinear models, so does this hold for nonlinear models as well? So we've done the similar experiments, but for nonlinear models which have redundant parameters, and we've shown that the results are the same. So the prediction and the prediction error variance will be the same if you have a nonlinear model with redundant parameters. And this can be formulated as a theorem. So for models with redundant parameters, the prediction error variance calculated using the linearization method is the same for the minimal representation as for the one with over-parameterized models. And that is the derivative of the non-canonical model with respect to its parameters times the covariance of the non-canonical parameters times the derivative of the non-canonical model with respect to its parameters transposed times the derivative of the canonical model with respect to its parameters times the covariance of the canonical parameters times the derivative of the canonical parameter with respect to its parameters transposed will be the same. But does this hold if we have more flexible models? So if we have a model which has more flexibility than the minimal representation. If we go back to this linear case, then we have a minimal representation with 3 basis functions. And then we'll have a non-canonical representation with 4 to 7 basis functions, where every extra basis function will add more flexibility to the model. Then we generate some signal using this minimal representation, and we'll perturbate the signal with noise again. And then we'll estimate the model for all these different realizations. The important part here is that new models will increase the flexibility of the model. So if we have the same experiments again, so on the left we have the prediction, and on the right we have the prediction error variance, and we have denoted that the rank of the information matrix will be how many basis functions we have. So if the rank is 3, we have 3 basis functions; is 4, we have 4 basis functions, and so on. And as one can see, the prediction looks the same, but if you study the prediction error variance, it seems that for the minimal representation, it will have a lower prediction error variance compared to the over-parameterized models. And this we can also formulate as a theorem, and I will omit the proof of the theorem in this presentation, but you can find it in the book if you're interested. So for models with linear parameters, with a model structure that is more flexible than the minimal representation, which is necessary to model the data, the prediction error variance for a more flexible model is larger or equal to the minimal representation. So that is, if you have the regression vector transpose times the covariance of the canonical parameters times the regressor vector of the canonical parameters is smaller than or equal to the regression vector time for the non-canonical representation times the covariance of the non-canonical parameters times the regressor of the non-canonical parameters. But again, neural networks are nonlinear models, so does it hold for them as well? So we've done some experiments where we've estimated the neural network with different number of hidden nodes in hidden nodes, and then we have varied them between 2 and 6. And 2 here is the minimal representation, while 3, 4, 5, and 6 will be in over-parameterized models. As you can see, it seems that the same will hold, that the prediction error variance is smallest for the smaller model, and it will be larger. But worth noticing here is that we have a quite small prediction error variance, or a small noise. So if we didn't have that, this might not be the true, since if you are close to the optimal solution, a nonlinear model could be well approximated by a linear model. So if we summarize what we've done with this over-parameterization, so for redundant parameters, the prediction error variance is the same as for the minimal representation, while for model with flexibility, the prediction error variance is at least not lower than for the minimal representation if we have over-parameterized models. So the thing we have to do to adjust our linearization method, or to extend it to over-parameterized models, we'll only change how we calculate the parameter covariance. So that is, instead of using the inverse of the information matrix, we have to use the pseudo-inverse, which is denoted with a plus sign here. But this is not the only way you could quantify the uncertainty in a model, or for example, neural networks. So two of the most common used approaches in the literature are either to calculate the variance of a mean from ensembles of models, or to include uncertainty as a prediction, uncertainty prediction as an additional output of the neural networks. And if we would calculate the variance and mean from an ensembles, this might lead to higher accuracy in the prediction, but it might be very computationally expensive, since already training a single realization of a neural network is expensive in itself. And therefore, people have come up with clever ways to create these ensembles, for example, using Monte Carlo dropout and Monte Carlo batch-norm, which are utilizing regularization techniques that are already used in the network. On the other hand, if you include uncertainty in the prediction as an additional output, this requires some assumption on the distribution of the prediction. If you know it, then it's good, but otherwise you further restrict your solutions. And this might also lead to more difficult optimization problems, which might not be desirable. So we will compare our method against these two methods now in the simulation and experimental study. In the simulation study, or the experiments comes from or inspired by autonomous driving, where we want to estimate the normalized traction force as a function of the wheel slip. And in advanced driving systems, ADAS, to estimate the tire road friction is central. For example, it can be used to calculate the braking distance, as seen in the earlier examples. But it might be difficult or expensive to measure the normalized traction force, which is calculated as the friction force divided by the normal force on the car. But luckily, the normalized traction force can be modeled as a function of the wheel slip. So we aim to train a neural network to predict this relationship between the normalized traction force and the wheel slip. So the experiments we have are from a car that's driving on snow. So we have some noise measurement Y, which can be seen on the right. And then we use a neural network to estimate the signal, seen in red here. And the estimate looks quite accurate. And then we will use to quantify the uncertainty of the prediction using this linearization method. And as one can see, it seems that we capture the uncertainty in the data quite well. But how does this compare to a neural network that learns its own uncertainty? So on the right, we have the same figure as before, but on the left, we have a neural network that learns its own uncertainty. And for that network, we have assumed that the likelihood of data is Gaussian distributed, and then we let the network predict the mean and the variance of the observations. And for the two methods, they both seems to predict the data quite well, and the prediction error variance seems to capture the uncertainty in the data. So how does this compare if compared to ensembles of networks? So then we have done the simulation study, which we have generated a signal which describe how normalized traction force depends on the wheel slip. And then we train a neural network to estimate that, and that will be our signal S. Then we will perturbate the output of the network with some noise. And then we'll train thousands of networks on these noisy signals to create our ensembles. And then we'll compare that to the linearization methods to the variance of the ensembles. What we've also done is we have leaved out some part of the training data in some regions to see the effect of predictions in regions without any training data, as well as the experiment is repeated for when we change the number of nodes in the hidden layer to see the effect of an over-parameterized model. So here on the left, you can see a minimal representation of the model, which is a neural network with 2 nodes in the hidden layer, while on the right, you see a network with 3 nodes in the hidden layer. And if you check in the prediction using the variance of the ensembles is seen in blue, and the prediction from the linearization method is seen in red. And all these individual realizations can be seen as the black dotted lines. And the region with training data is marked with this gray box. So if we study the prediction and prediction error variance in regions where we have training data, it seems that we get the same prediction error variance and prediction for these two methods. While if we check in regions without any training data, for the over-parameterized models, it seems that the linearization method underestimates the prediction error variance. So that is, we are too confident in our model. And that can be seen since the red line is inside of the blue line in that case. But this leads to another questions. Are neural networks the best model for these tasks? Or are neural networks the best model to represent the tire road friction relationships? So what we have done, we have compared the models to other models with other model structures. In the thesis, it's a couple of them covered, but here I will cover 3 of them. So the 3 I will cover in this presentation is the parametric model given by the magic tire formula with a bias term. And the magic tire formula comes from modeling of the tie rod friction, which has been done through experiments and physical laws over decades. And when we have included this bias term, since if you have noise and measurement, it might not be that a normalized traction, that zero slips gives zero normalized traction force, which the model assumes. Then we'll compare to black box models that is linear in parameters. Here the Chebyshev polynomials, which are quite nice since their basis functions are orthogonal to each other. And for these two models, we will quantify the uncertainty in the predictions using this linearization method. And then for the third one, we have Gaussian processes with squared exponential kernel, which is a non-parametric model. So to get the prediction error variance for that model, we will just sample from the posterior. So here you can see the prediction and prediction error variance for all these models. So first you have magic tire formula with the bias, Gaussian processes, Chebyshev polynomials, and the neural networks with the linearization method. And all the models give a similar model fit around 70%. And if you check the prediction error variance, all of them seem to capture the uncertainty in the output quite well. So what have we shown in this thesis and in this presentation? So we have presented a method to quantify the uncertainty in the predictions of neural networks and compared it to other methods that are commonly used in literature with similar results. Then we've shown that ambiguities in neural networks and redundant parameters can be neglected when we are interested in the prediction error variance. And then we also compared neural networks to other models, and they gave similar results, both the prediction error and the prediction error variance, when we were modeling the normalized traction force as a function of the wheel slip. Thank you for listening, and please, if you have any questions, you can ask them after the opposition.
So, thank you, Magnus. And before we proceed with the discussion, we will have a short break. So we'll be back in 5 minutes. So welcome back. Now we'll move to the main discussion, which will be led by Professor Håkan Hjalmarsson. So please, Håkan.
Okay. So thank you, Magnus, for the nice presentation. Yeah, I'm Håkan Hjalmarsson then from Division and Decision and Control Systems at KTH. So it's been very interesting to read your thesis, Magnus, and this has been a bit going down memory lane because in 1993 was this thesis. And that was also about model uncertainty and dealing with that. And in my thesis, I had an example of a steam engine from the lab in Linköping. So I don't know if it still exists. It's not this exactly this one, but there was a steam engine. So I don't know if it's still there. Probably not. This is a long time ago. Yeah, so now we are here in 2021, 28 years later, and you're talking about completely different applications, autonomous driving. So my first question here, would you rather have made your thesis in 1993 or now?
I guess for me it would be impossible to do it in 1993.
Imagine you could go back in time here.
Yeah, I guess I think like to do it now, you have more, you can get more powerful computation power, which I think is quite neat. So in that sense, I would rather do it now. But then again, if I did it in 1993, probably it could have been more impactful, since then we already seen the results of it now, hopefully.
Yeah. Okay, thanks. Then I had a more general question here. What is research about?
It's a hard question.
We could spend a whole hour here discussing
yes.
this.
Exactly. No, but I would say to explore something new, try to find something a problem you want to investigate more, and try to find not the solution, but the answer to why it doesn't work. So if you have something that you think should work, or you want it to show that you could get further on with something, you want to, maybe it fails. So you are interested in why does it fail, or how can I explain that it fails?
Mm-hmm. Yeah. Is there some other major aspect of research if you think about the word?
I guess search to search for something interesting.
Search is something, but you also have the preposition there.
Yeah, look what people have done before as well.
Yeah.
And take that in, to build on to what people know beforehand.
Yeah. So that's certainly also an important part of research, which we'll come back to a little bit. Okay. So here is. I got two versions of your thesis, one printed and first I got a PDF version. And just this morning I discovered that they are not the same. So what has happened?
I thank you for noticing. I also noticed it this morning. I don't know. I guess something went wrong in the printing, because I checked the PDF I sent and it's the same as the PDF version.
Yeah. Yeah, so maybe you need to renegotiate the contract with the printer.
Exactly.
I can tell you, I had the same problem. So it was an exam. It was 200 students. So I sent my PDF to the administration. They printed it. And then after half an hour into the exam, I started getting calls that the students don't understand the figures. And I said, oh, the figures are perfect. There's no problem with them. I looked at the PDF I had on the computer. Problem. And then they continued to complain. So I had to go down to meet the students. And then I could see that the figures were just completely different. They were actually real figures with curves and so on, but they were not the curves I had put in. So, yeah. So sorry that you had to experience this. Okay, now, I mean, you mentioned autonomous driving, and you also had this in the presentation. So that's obviously like a killer application here. And you gave a nice example there with the moose. Can you give some other examples of how using uncertainty could improve safety in autonomous driving? Have you thought about this?
I mean, if you take for the other example with this stop sign that you misclassified as a speed limit sign, yeah. Probably that was just that it got over the hump for the speed limit sign. So if you had some uncertainty, probably you would have like redo the calculation or something to see that it actually was a misclassification. So in that sense, if you would include some uncertainty, you would get rid of these, probably some of the adversarial attacks you could use on networks.
Mm. Okay. And now to incorporate, I mean, your thesis is about this, and I mean, of course, that's only part of the way here. So what are the main challenges now, if you would like to incorporate and use actually how to use this uncertainty? I mean, again, we go back to your example where it was relatively easy, but what do you see as the main challenges you look at this picture? I mean, it's a very complex world, and adding then uncertainties here makes it even more complex. So what do you see as the main scientific challenges?
So if you take just implementation-wise of the method I suggested, a real big problem is that you will get really large matrices for the covariance.
Yes, but I will come back to that. I was
okay, yeah.
In terms of how to use. Suppose you could compute now the uncertainties, but what would the challenge be then?
Then the idea
in terms of decision making.
Yes. So in that case, you probably have a lot of sensors. You can get like one from the camera, one from some LiDAR sensor and from distance. Then the main challenge would be to combine this measurement so you get some better understanding. So say that you have a very uncertain camera image, but you have a good LiDAR image. Then you would rather combine this image to get the best as possible prediction of what was in front of you. So say that the camera says that it might be a car or it might be a person, but the LiDAR is very certain that it is a person. So then probably if you combine these two, you will get that it's a person. Mm. So I guess that's the...
combination of all the information with uncertainties now, then will be sort of, yeah, I tend to agree here. So let's now dive into the thesis, getting a little bit more technical here. So here you have an expression for the parameter covariance matrix, which looks a bit complicated. I mean, it's 3 factors with the inverses, and then you have some Q matrix there. And you have a theorem saying that this is actually the asymptotic covariance matrix. And for the proof, you refer to a paper by Lennart Jung and Peter Keynes. So my question here is, do they treat the setting that you have?
They are more to dynamic systems, while I have a more of a static system, I would say. But if you think of neural networks with discrete activation nonlinearities, then you have to do some adjustments. But if you have some continuous activation functions, I would say it's quite similar setting.
It's a long time since I looked at that paper. I certainly have read it, but my poor memory says that it was for linear systems. Is that correct?
I think this is for nonlinear, if I don't misunderstood the paper, because I think if you check the system identification book, he referred to this paper for the nonlinear case.
Okay. Yeah.
But I might be mistaken.
Yeah, I couldn't recover it now, so I can't say yes. And this is just my poor memory. You're probably right here. Okay. We'll look a little bit more into this expression, although I think your conclusion in the thesis is that it's not necessary to work with this complicated expression because the model error which you call is smaller than the sort of variance error here. But anyway, I think it's good to look at this. So if we take the linear regression case, then you have, assuming we have the true system like this, this is sort of the interesting signal, and then you have white noise, and then we have a linear regression model like this, and then this expression should be valid, right, to compute the variance of theta. So then we were interested in this Q factor here. So we compute the derivative then of the cost function. So it would be this expression here, right? This is the residual, and then times the regressor. And then we just plug in y, meaning these 2 terms, and we get the corresponding 2 terms over here, right?
Yeah, but I guess I guess in my thesis I used the mean squared error, but I guess it's the same if you use, because this is instrumental variable, right?
Oh, this is least squares.
Okay.
Right. This is the error, and then times 5.
Oh yeah. Sorry, I missed the derivative. I thought it. Sorry,
it's the derivative. This is the derivative. Yeah. So it's what we have in the Q matrix here.
Yes.
And then my question now is now when we form Q, you take this expression that we have here on the right, you take it transpose and multiply together, and then you take the expectation. And then I'm wondering, what variables are you taking the expectation over now when you do this calculation of Q?
Yeah, so it's the measurement noise you take the expectation over, and then you have this 1 over n to take if you have some non-stochastic properties.
So it's only over the noise here, E.
Yes, if it's a pure expectation, I would say so. I think.
You then need this whole expression. What is Q in that case?
Then I guess Q will be the same as for the when you have the true system in the models. Then it will just be these two transposed each other.
So if you think about it, this is white E, so when you take it multiply with this cross term, it will be 0.
Yeah.
And then you take the expectation, so the other term will disappear. No.
Yeah, you're correct.
So the point I'm trying to make is that there are two different cases here. Either you look at case with E, you take the expectation all over E, and then this expression actually reduces to the one without any model error, because this term is deterministic. Yeah. And this one will disappear because that's how the theta limit here, the theta c star is defined. So this will disappear. But if you consider now the case where you for different experiments draw different realizations of y0 as well, then you will get another expression and of Q, and you will get a different variance. So it has to do with what are you after when you do when you compute the variance here of the estimates. You want to take into account only the variability of the measurements, or also the variability of what you are interested in. Then you get two different answers here. So question is if this matter what you do, and yeah, do you have any comment on that?
I guess for the simulation study I have made in this thesis, it doesn't matter, since then you will assume that this first term will be 0, since you will have it in the model set. Otherwise, I guess it would matter.
Yeah. So it has to do with what you're interested in what type of uncertainty, and I guess that can also be, if you look at different applications, it can be important. So that brought me to the question: how are the Monte Carlo simulations done? Are you using the same X for the different simulations, or do you draw different X's for the different realizations? Or is it just the E that is varied over the
It's the same. It's just E that is varied. It's the same X for all the realizations.
Yeah. So then this expression then simplifies, and although I mean you already had that the error of due to the under modeling is small, so it probably would not be any noticeable difference. Okay. Anyway, I'm sort of stuck on this expression. So in the simple case, or in your case, then this estimate is good. This taking your psi transpose psi and invert it, that gives you a good estimate of the covariance matrix. But what about if you have this little bit more complicated situation? Do you know about any estimates of P for this case?
I haven't looked into that yet, at least. I've sort of thought about it, but not gone through it.
Yeah. So there is actually some work done there, going back to the 90s. So here is something, and the reason I bring this up is that I think this also applies in your setting. So let me explain what it is. So theta hat lambda, that's a recursive estimate, recursive least squares estimate with forgetting factor, lambda. So lambda is something, it makes this estimate forgets past data at this rate with lambda. And then if you form the sample covariance of these sequence of estimates over time, normalize it properly, it will converge to the covariance matrix. So the point is that you can see this estimate at time k as just taking data over a window backwards in time. And then you form a sample estimate of the covariance using this sequence. So the theta bar here is just the mean of all the past estimates. So this applies in both cases to estimate P. So my first question here, does this method fall into any of the methods that you have examined in your thesis?
I wonder if it could fall into this ensemble techniques, because then you're sort of calculating at least this theta bar I.
Yeah.
But then you should also compare to the one you have in this last iteration as well. Or get that you should. Or no, because it's taking over samples, right? This.
Yes.
Yeah. Maybe you could adjust it for it, but I could say. I guess there is suggested that you could like sample if you train a model and you just sample it in the last iterations, how the parameters change. Then I get, oh no, sorry. Yes, this falls probably into the Bayesian neural networks, which I examine in the thesis, where you sample from the posterior.
Yeah, that I didn't think about. That's could be one way to see it. I was more thinking in terms of this ensemble that okay, we use like batches of data here to form the estimate, and then we estimate them. But yeah, that's an interesting interpretation. Good. So the question I have now is would it be worth to try to extend this to the neural network case? Because we know how to do a recursive estimation for nonlinear models as well.
I would say it would be interesting, because then you can also see that maybe how many data points do you use. You can use it in the training to maybe speed up the training as well. Or like to improve, if you do something recursively, you can improve the prediction over time.
So here it seems to me you get this covariance matrix for free. You don't need to do anything more than sort of recursive estimation. Okay, let's move on. Then you discussed in the presentation this case with redundant parameters. So you have two cases with a canonical model, and then you have another model with more parameters, but that don't really give anything new. And then you get the same, actually exactly the same estimate, the predictor. And then you get the same covariance also of the predictions. And what I was so clear to me was that this depends on that the range of the model structures are the same. And I couldn't really find the definition of this. So could you explain what you mean? Maybe I missed the definition, but maybe you explain what you mean here, but the range of the model structures are the same.
I guess it's sort of that the model, the set of models will be within, the bonus will be in the same model set. I guess would be an explanation. I don't think I maybe stated super
because I thought about the predictors, but I mean all, no matter how you parameterize it, you can always predict anything in R on the real line. So I couldn't see that making a difference between this case and when you have additional degrees of freedom that you could consider later. So it was not really clear to me what you meant here with the range of the model structures. But yeah.
Now, I would say that they are the same expressiveness. I guess it's easier to visualize if you think of polynomials, so that if the same range of model structure, then you would have a polynomial with degree 2, but you would have three different basis functions you can use.
So you have a linear dependency there.
Yes, exactly.
Yeah. Then a side issue here. You prove this that the variances are the same. But based on this 525A, do you really need to prove anything? Or
let me just check 525.
Yeah. If the predictions are the same, shouldn't the variances be the same?
I don't think it necessarily need to be that. I think if you go back to we talked about the nonlinear case when we plot the covariance. I think it's interesting to check that it's the same in all these different clusters, so depending on the ambiguities. So I mean, you could have some parameters that are very uncertain in one case, and that this transformation matrix will cancel out these eigenvalues that are 0.
Mm-hmm. But if the predictions are exactly the same with different methods, wouldn't the variances of these two predictors be exactly the same?
Yeah, might be the case.
Something to.
I'm not sure.
I mean, in any case, you proved it, so there's nothing with the proof. In the presentation, you had this with the 8 different clusters. Is there some fundamental difference between that case and this case that we have on the screen?
So the fundamental difference is that when you have these 8 different clusters, all the parameters are equal and expressive, but they all are needed to model the data. So in this case, you could sort of remove one basis function and you would give the same prediction. So if you think of, take polynomials again, if you have that, have 1 x squared x and 1 minus x squared. If you remove this last one, you can still get the same prediction as if you would keep that one. But in the case of neural networks, if you would remove one of these theta, you will not gain the same predictions. You won't get these clusters then.
If you think in terms of identifiability.
Yeah. I guess that's is sort of the problem here, is that you will have something that is unidentifiable, while in the case of the clusters, you have something that is locally identifiable.
Exactly. Yeah. And then actually you sort of motivated the importance here when you have neural networks and within these clusters. So I don't know if you want to add anything to this, or you basically cover this.
No, I guess not as much. I guess I can add, as repeat that I said before. I think if they should be viable in this autonomous driving, they should have some estimate of the uncertainty, so you can counteract it for it.
Are you aware of any related work when you go back to what you had here?
You mean on to show that for the redundant parameter case?
Yeah.
I haven't at least seen any that I know of.
Yeah. Would you like to see something?
Yes, please.
I'm naughty here, but it goes back to research, what we discussed in the beginning there. That, I mean, it's good to look back also, and I think it's important, or as important actually as looking forward to also, because you learn a lot quicker than. So here is a result from Peter Stoica and Söderström. So you have an estimate theta. You minimize some cost function, and then you have a function, and then you have another parameter alpha that also parameterizes your problem then. And then you can re-parameterize your cost function so that then you can estimate alpha directly. And then what they show is that the estimate you get in that case of alpha is the same as first computing theta hat and then applying the function f. So you get f of theta hat. And that's exactly the same as directly minimizing alpha. So in your case here now, I mean, you have in the linear case, you have these two model structures, and the theta hat is in your case theta I, and then you have your canonical model, which is a linear function of theta I, and that's your alpha here. And then you just apply this theorem, and you get exactly, I hope I'm correct, what you have here. So I'm not going to go through this details. Yeah, in fact, I think there is there that would be of interest for you. There are also some other work of interest that I like to mention. So Stoica and Marcetta worked on singular information matrices. So I think that's also what you have in this case with you have linear dependencies in phi. So that could also be of interest to you. Another thing is in statistics, one used this notion of degrees of freedom to denote the effective number of parameters. And then if you have more parameters then the model that can be expressed by I mean the model, then the degrees of freedom doesn't change. So that's also the same notion. So I think it could be interesting to go back to these also, these works. Okay. Then we go to this other case where you have sort of over parameterization. So the nice thing with what we saw earlier is that, I mean, even if you have more parameters, you're not really hurt by it. That's a nice thing. But here now, if you use more parameter in this case than necessary, then as you have shown, you get a bigger variance. So could you first comment a little bit about what role does this play now in applications?
So I mean, in some sense, this would push forward to use as small models as possible. So an idea would be that you start with a large model and you will decrease to get the best size. And I guess that for application purpose, it's maybe you get more uncertainty if you have a large model. So if you want something to take this uncertainty in considerations, you would rather have a small model so you get these small uncertainties in the prediction. But I guess the problem is that if you have too small, you get this bias term. So it's quite hard.
And how would you go about and find a good balance then?
I think personally I will go for a bit larger model, and then I will try to, as seen in the later part when you get an overconfident for overparameterized models, I would try to have some other sensor to help me as well that maybe are more confident in that region. So you will split your.
And how would you know you have an overparameterized model in the first place?
Like, I guess the brute force ways you can do this simulation where you decrease the degree of freedom all the time until you find a minimal one which have the same prediction. But that could be very time consuming. So I guess I would always assume that I have an overparameterized model instead.
But can you be sure of that, that you have an overparameterized model to begin with?
I guess not. If you don't try different model orders, I guess you don't know if it's over parameterized the one you start with.
You would look at the prediction errors, or yeah.
Yeah, like, I guess you can look at the prediction error variance if it starts to go very large where you don't have any training data. That would suggest you to have something that is over parameterized. So if it's increased, because then you have some more flexibility than are necessary to model the data.
Any related work here?
For the do you mean to how to handle over parameterized?
Yeah, this theorem that you.
Yeah, for the theorem.
Yeah.
I've looked and I didn't find any like that proves the theorem, but I guess it's very similar to this bias variance trade-off which people talk about. Since you talked about that you will get lower, if you have more data, you will get a lower variance.
Yeah, so would you like to know about some related?
Yes, yes, please.
So this was a work again from the 90s, and maybe you recognize one of the authors here. Or both. So this is the least squares problem. R here is your phi transpose, and K is the order. Oh, this is in the frequency domain. So W is in the frequency domain, but it basically has the same structure. So phi k plus 1 is an extension of phi. Phi k plus 1 is an extension of phi. Wk plus 1 is an extension of wk, as you could see phi m here being an extension of phi cm. And then you can find this expression here saying that what we have here, which corresponds to this, is what we have on the left plus a positive term. But it's for a special case here. So yeah, but it could be maybe also of interest to you to have a look there. What about nonlinear regression? Because this is for the linear case, and you do some sort of empirical observations there, but can you prove anything, you think?
No, I couldn't prove anything, because you get this problem that if, as I think as stated in the presentation, if you are close to the optimum, this linear approximation is good of a nonlinear system. But otherwise, I don't know how to prove that it's true.
Yeah. Would you like to know? No, I'm kidding. I don't have anything there. So I think this is an open problem. However, there is, you're right about this, you at the bottom here you say if the prediction error is small, this would be true for a nonlinear model, which I guess what you also talked about. But I'm not sure I follow. Why is the size of the prediction error now critical for this result?
Or it's rather that the noise that you get from the signals, or it's the prediction error is, you can see also how close are you to the optimal solution of the parameters. And if you think of that, you have a very flexible model, so you can model it perfectly, then you should get a very, very small prediction error variance. You should be very close to the true signal.
So it's rather the error in the model, in the parameters, rather than the prediction error, right? That's what you meant when you wrote this. Yeah. Okay, then we are on the same line. Thank you. Here is something that is not in your thesis, but I very much would like to have your opinion about. We all know about this overtraining. So here is an example now. You on the x-axis, we have the number of parameters. Here we see the training error, which goes down monotonically when you add more and more parameters. And then when we look at validation data, we know that the error goes down with more parameters, and then it starts to go up. So this, when you look in Lennart Ljung's book, for example, This is what we see. But now people start to claim that, well, it goes up, but then after a while, it starts to go down again. And then you get even here better fit than for this sort of optimal model that you would think is here, but here taking more and more. And actually you are here using more parameters than data points. So first, have you seen these type of results before?
I haven't seen it, and my gut feeling is it feels strange. It feels that probably because if you have more parameters than models, then you should have a parameter for every data point, sort of.
So this is now a super hot topic here. So do you believe in it? It seems you don't believe in the curves here.
I mean, I believe that you can probably get these results, but probably it is because you get some very, you really fit one line to every data point. Or this might be the problem also that you have some very stochasticity when you train the network. So probably it could be that if you just use a good realizations, you could probably show this as well if you're.
But this is on validation data, so you have not used the data to train your system.
No, but I mean, if you probably train. I don't know how they did it, but you can train a lot of models, and then you may make it bit different results every time you train them, and then you just pick the best model that you trained for this specific case. Yeah, I guess it could be one thing.
Pick best. I don't think they are cheating in that way.
No, I don't say that they are cheating, but I guess that's why you could get results that you would not expect. Because I guess if you would repeat this experiment 1,000 times, maybe you wouldn't get this same results.
Yeah, but I think that's what they get. So.
Okay.
I have not studied this to any other than just glancing at this paper, and I mean now a paper is piling up on this topic because it looks now we have a completely new result that I mean our textbooks only tells us first part of the story here going on in this range, but then there's a lot more interesting things happening here. Yeah, so you have already expanded on your topic, so I'm not sure we get any further here, but it certainly seems to relate to what you're doing, since you're discussing this when you now are going to expand out a neural network to many parameters and maybe a deep network and so on. So this looks relevant here. Okay, then we come to the approach you have taken to linearize the problem, and I think this is what you mean. You get an underestimate, you get a good estimate where you have data, and then you get a poor estimate, an underestimate of the uncertainty where you don't have training data in case of overfitting. So is this the case? That right?
I guess it's the case you're pointing at, but the picture should not show that. So that this picture is rather to show how many data points you need for asymptotic results to hold.
Yes.
So if you're interested in that, it's rather the plot 6-4 that would be interesting. 6-4 or 6-3A, 6-3B. So the one I used in the presentation.
Yes.
So these are more like this one is this one should converge to the plot 6-3A.
Yeah. Okay. Yeah, I picked the wrong plot, but
the idea is the same. Exactly.
Yeah, but and do you have any intuition now for why should it be underestimating? Because I don't see that you mention anything really about why.
I guess my intuition would say that since you compare to ensembles of realizations, then really those, and if you have extra flexibility, you can fit very good to the models. And then maybe when you don't have any training data, it will diverge. But this linearization method will not take this in consideration. So that will think of one realization, and then you try to linearize around that realization instead.
Okay. I looked at some other picture, and then I got the notion that you're a little bit pessimistic, because is it not, here it's not so bad, is it?
No, here it's not so bad. I agree.
So I think, I mean, you were a little bit pessimistic there on how it can handle when you're out of the data range. But I don't know if you can have seen any pattern on when you get a fairly good representation of the uncertainty as here, or when you do not, as in the figures you referred to earlier.
I guess as more parameters you add, the more over parameterized the model will be, the poorer the linearization method will perform. And then it's also quite important to, like when you do this realization, to pick the best parameter in some sense when you train. Also.
Okay.
But as answer, I guess the question is rather that when you have more over parameterization, you see this more clearly than when you don't have as much over parameterization.
Okay. Then we have the experimental study, and there, as you also said in the presentation, I mean, you observe, you get pretty similar results. I didn't include all the figures you have for different methods. Have you any explanation to why this is the case?
For the experimental study, a lot of the uncertainty is in the noise of data. So that's why the size is quite the same. So it's very dominating by the noise of the prediction error. Okay. Otherwise, you have some results that shows, for example, if you compare the neural networks to Gaussian processes, that they should converge when you have a lot of layers. And as well, that you've shown that you can represent Gaussian processes with a finite number of orthogonal polynomials, for example, the Laplacian polynomials. So I guess that also motivate the similarities.
So when you look at the polynomial cases, they look basically identical.
Yes.
Right?
I mean, I guess you can see like Chebyshev polynomial as Chebyshev polynomial is improvement of the normal polynomial in some sense. So you should need less basis function, but they should be sort of coincide. For Laplacian, they are more like Fourier series expansion. So I don't know why they also coincide.
So these different cases do not use the same basis.
No, there's not, at least between the Laplacian and the other two. So they're not the same basis.
But I mean, you can't get one from the other.
Not for I don't think you can get between the Laplacian and the other two. If you don't do some expansion, since you have this sinus term, so I guess you have to do some Sears expansion, then you can get it with infinite amount of terms.
But the Chebyshev and the standard monomial,
they are sort of subclass of each other. But I guess the interesting part is you have to use fewer Chebyshev polynomials, since they are constructed in a better way.
Okay. Another thing that came to my mind there is which I guess is a relevance now when comparing different methods is the computational times here. How do they differ?
I would say polynomials are super fast, while the network's not that fast. Gaussian processes is quite fast as well. But that is because I used the implementation of MATLAB, while have sort of done my own, maybe not the optimal implementation of the networks.
Mm. And when you scale this up, will this be the same? Will it? How do they scale these different approaches in time?
I mean, if you don't consider to calculate the parameter covariance, so you don't consider the inversion of the matrix, then I guess the non-linear models might scale better in some sense, since you will successfully iterate them, while for the polynomials, the linear and the parameter, you will get a very large matrix to invert.
Mm.
But since you will still need to do that to get the prediction error variance for the nonlinear models, you have to come up with some smart ways to do this. Otherwise, it will be more otherwise it will be more efficient with the linear models.
Or if you estimate the variance directly, or
yeah, exactly. If I estimate the variance directly, then it will be faster than to calculate if I have too many parameters.
Yeah, you bring up this with the matrix inversion. So in chapter 7, you have some conclusions. I try to summarize here that you see that this linearization provides similar results as these other methods that maybe look more advanced, but linearization works fine. But you also notice a challenge with you have a large matrix to invert, you have a non-unique parameterization, you have over-modeling, then you also discuss regularization. And is this a matrix inversion sort of the key problem that you see now?
I would say for the linearization to be valid, I would say that's the key problem. And I guess there are like multiple ways you could solve this. So either you could do some, try to approximate the covariance matrix and to make it maybe like a diagonal matrix to invert, or you update it in successive ways. Or you could try to, you could think of the I think I have some examples early in the thesis where you think of the output of the network as some nonlinear basis function. So then you say that the network learns the basis function, then you would calculate the covariance of those basis functions. Because then you will get a smaller covariance, then you will get a much fewer parameters and a smaller covariance to invert.
Yeah, so this leads me to this question here, that if you can characterize this covariance matrix in some alternative ways. So that seems to be one way then. Have you thought of any alternatives for this?
You mean to compute the covariance matrix?
Yeah, to compute this expression here that we see here, where P now is P is, I mean, this matrix inverse. So in the linear case, I mean, in the non-linearity, it's more complex.
Damn, now I forgot the name for it. But yeah, I think I've seen some papers where you because in the optimization algorithms, usually you do some approximation of this Hessian of the cost function, which is the inverse of the.
Yeah.
So from the inverse of the Hessian, you can get the parameter covariance. So I guess you can if you can use that to calculate or do you mean to? I guess you can do some. Or is a conjugate gradient method to approximate the inverse. You can successfully update it over the iterations. So you start with some diagonal matrix and then you will add on some to get fast, so you don't have to invert the full matrix.
Yeah, so yeah, I guess the lots of techniques here building on the optimization, which basically needs this matrix inverse as well to be efficient, but not all methods, of course, use it. I had some thoughts I'd like to share on this topic that like to hear your opinion about. So here we have a least squares problem. Theta are the parameters, so we estimate theta using least squares, and then you get the predictor looking like this. Yes, you recognize this. So what we see here, this phi transpose can be seen like some kind of inner product, and then you have y phi here, which is also like an inner product. So you can formulate this quite abstractly I mean, it's a projection problem. So you can formulate it in terms of inner products. So this strange notation now with this thing here, it means an inner product. So it's exactly the same expression as you have here, but now expressed in terms of inner products. So why do I bring this up? Yes, because if we now take the norm squared of this projection, I take this times itself, then what I get is this expression. So this on the left is the norm squared now of my projection of f, looking like that. So now if we compare with what you have, which is what we have here in the middle, it would be has some resemblance to what we have here, except that you have the f prime, and here there's some inner product. But suppose you can find a function now gamma, so that this f prime is an inner product between phi and this gamma. Then the expression you have here is the norm squared of this function gamma projected onto the space spanned by phi. We shouldn't go in too much into the details, but it's in the least squares case, it's the row space of this matrix phi that we project on. And then it's the norm squared of that. So what this means is that the problem here of computing a matrix inverse and then multiplying with things from left and right is basically the same as you need to compute the projection and then take the norm squared of that. And that tells you now, if you want to do approximations, maybe you don't, if you project on a smaller space, then you will get something bigger. So you get an overestimate of what you have. And then maybe you can play around with that and simplify the computations. You find a clever space to project on, and then you get an overestimate which is cheap to compute. And that maybe is enough for a particular application. So this is something that might be useful.
It sounds very interesting.
Yeah, the question is if this could be something to look into. It has been done very thoroughly in the linear case.
I would definitely say this could be something to look into.
Another view of this is the following. So I mean, you're interested in variance, but basically you're interested in uncertainty. So if you look at the confidence interval, I mean, there you don't need to compute the inverse to check if a point belongs to a confidence region. You just need the Hessian. So to check if a theta belongs to this set, you just need some matrix multiplication. To figure out what the boundaries, that's a more complicated problem. Then you need to basically invert the matrix or compute the eigenvectors and so on. But just to check if a point is inside or outside, that's very easy. So that I don't know if you have been thinking about that, if you can use that in some way.
Yeah, I haven't thought that much about it, but I guess you could, as you said, you could do the same thing, and you could, if you check the parameters. I guess the problem is you need this theta 0. But I guess you can live with all those as well.
Your
So,
theta hat, you replace it with an estimate. So,
yeah.
so the typical way we do it, right? So you plug in the nominal estimate, but then you check if theta, another theta could be inside this. Then you could just check if this is condition is satisfied.
Yeah, I would say you could. This sounds also like an interesting idea to do it, since then you don't have to calculate.
In fact, you don't even have to do this, because what is a confidence ellipsoid? Well, if we think about, I mean, that you're close to the optimum point, then if you do a second order Taylor expansion of the cost function, you're minimizing. I mean, you get something like this, because the gradient is zero at the optimum, right? So what we have here in the expression for the confidence ellipse or region is just the cost function. So to check if a given point theta belongs to a confidence region or not, it's sufficient to evaluate the prediction errors. So then you can check if it's in the confidence region or not. So it's extremely simple to do this. Yeah, so food for thought here. I mean, I don't expect any real reactions. We're coming to the end of the discussion also. So, but maybe something to take with you. I don't know. I mean, this is what I could think about when I thought about.
Thanks. I will look into this.
So we're approaching the end here now. So coming back to your killer application, what is the next step now from your perspective?
I think we'll look into how to both try to estimate this covariance in a cheaper way, for example, using some from the optimizer or something, and also how to combine, if you have some diffuse measurement from different sensors or different time instances in some sense. I would say.
Yeah. And I mean, we also brought up this black box versus gray box issue, and we see, I mean, black box tends to be very sensitive then when you don't have appropriate training data. So but you think that going full black box is the way forward when you look at the scenario like we have on the screen?
No, I think you should do some combination. You should have some gray box model in the back end, which you adjust with some black box models. So you combine those two together, I would say, is the best way. And I guess that you can sort of do with this. If you have some confidence in your gray box models and your confidence in your black box models, then you can combine those to get the best out of two worlds.
Mm-hmm. And I mean, we went back 28 years. The final here. Where are we 28 years ahead?
If we talk with autonomous driving, I guess we will have a lot of autonomous systems rolling on our road. And I think that probably it will be incorporate this uncertainty for those. So I don't know what will be the next step in the research questions by then. Yeah. But I will look forward to see it.
Okay. So to summarize here, thank you very much, Magnus. I mean, I think you have a very relevant topic if you look at this type of applications. We've seen it's an old topic and much is known, so it's a good idea to benefit from this, so that then you can focus on the new challenges. And from the thesis, I see also that, I mean, now you have acquired a very solid background, so I think you have a good conditions now here, and it was nicely written, is easy to follow, and also a very thorough study, I think. You gave a nice overview of different methods, and you made a comparison and used experimental data. So I think you don't see that often to do this kind of thorough studies, and so I appreciate that. And along the way here, you have identified some important challenges, for example, with these high dimensional computations. The double dip was not in the thesis, but maybe that is something to think about.
Might be included in the follow-up.
Yeah. So congratulations, Magnus. Thank you.
Yeah, thanks.
Thank you, Håkan. And that we open up for questions from the rest of the audience. So please use the chat to submit such questions. And Magnus' co-supervisor, Daniel Axehill, will assist by reading those questions.
So we have already got one question from Daniel Jung. Yes. And the question is, do you have any idea of how to extend your methods to capture that the neural network have different uncertainties in different operating conditions? For example, in regions with less training data, or simply that there are more disturbances during some ranges of collected training data?
I guess you. I guess when you check this uncertainty where you don't have any training, you will see that you have a larger uncertainty. So I guess what you could use this for is to know where to collect the next point of data. So say that you want to collect more, you're running a test continuously, then you see that, okay, here we have bad uncertainties in our prediction. Then we will move towards that region to calculate, to collect data from there. I hope I answered the question.
Yeah, so are there any more questions?
While we're waiting, I guess I could sneak in and give you a question myself. So you presented uncertainty in your thesis in problems where it wasn't too difficult to present it for the user because of the lower dimension. But neural networks are often used for high dimensional problems. So you have any thoughts about how to present the uncertainty? You can choose any high dimensional application if you want to simplify this.
If you think of, I guess, like images is a good place to think in. You could probably use some color code to show it to the user. Or if you have a system with multiple inputs, you could show one plot per input, sort of, to see how uncertain it is in some regions. But I would guess the color code is an easier way for a user to interpret the uncertainties. So either blur out the picture or something like that.
Yeah, well, I don't know, but it sounds reasonable to me.
I haven't got any more questions in the chat window.
Okay, if there are no other questions, then we end this part of the seminar. What will happen now is that I will meet with the opponent and the supervisors to discuss the thesis and the presentation and make a conclusion. And then we'll get back to you here in a short while with the outcome of this meeting. So thanks for now. So welcome back again. We've had a brief meeting where I've listened to the opponent and the supervisors. And after that, I have come to the conclusion that I want to pass Magnus on the thesis and the thesis presentation. So congratulations.
Thanks.
Well done.
Thank you.
Gratis.
Thanks. Tack så mycket.
And I would also like to thank the opponent, Håkan Hjalmarsson, for an excellent opposition here. And I enjoyed your comments and suggestions a lot. So
congratulations, Magnus. Was a pleasure to be part of this.
Yeah, and thank you for the very good comments and ideas.
And finally, I would also like to thank Pavisbo Nibel for assisting with the technical aspects of this seminar. And with that, we end this licentiate presentation. So thank you everyone for attending, and goodbye.